Well, students, we are going to discuss triple integration. But before that, for triple integration, we need to learn three-dimensional coordinate system, which is required to evaluate certain triple integrations, transformation of Cartesian to polar, spherical polar, and cylindrical polar coordinates. So first, we shall see three-dimensional coordinate system. Now, if you observe here, so I have drawn the figure. Now, if you observe in the figure, we are having three-dimensional coordinate system, three axes there, x, y, and z. So it can be extended. This is negative z, this is negative y, and this is negative x, that is on backside. So I take some point p, x, y, z in three-dimensional coordinate system. These x, y, z are called Cartesian coordinates. Then corresponding r, theta, and phi are called spherical polar coordinates, and rho, phi, and z with usual notations are called cylindrical polar coordinates. So these are Cartesian, these are spherical polar and cylindrical polar coordinates, rho, phi, and z. Now I draw perpendicular in XOY plane. So that is at T. T is the foot of the perpendicular. Now its coordinates are x, y, and 0. Now here if you observe the significance of x, y, and z, x means it is OT. Then TM is y, similarly ON, and PT is equal to Z. That's what I have written here. OP is equal to R. Theta is angle made by this OP with Z axis. Then phi is this angle made by OT with X axis. OT is equal to rho. Then PT is equal to Z, and so on. So this I have described here. Now we shall see. If you observe this three-dimensional coordinate system, x, y, and z, in Cartesian coordinates in two dimension, so it divides the whole plane into four equal parts. Each of the part is called quadrant. First quadrant, second quadrant, third quadrant, and fourth quadrant. Now here, three-dimensional coordinate system, it divides the whole space into 8 equal parts, and each of the part is called octant. Each of the part is called octant. Now, relation between this Cartesian and spherical polar coordinates. So this can be obtained from this figure. X is equal to r sine theta cos phi, y is equal to r sine theta sin phi, z is equal to r cos theta. If you square and add, you are getting x square plus y square plus z square is equal to r. Therefore, r is equal to root of x square plus y square plus z square. Similarly, Cartesian to cylindrical polar coordinates. So these are the relations there. X is equal to rho cos phi, y is equal to rho sin phi, z is equal to z, and x square plus y square. If you square and add, you are getting x square plus y square is equal to rho square, because cos square plus sin square it is 1. So rho is equal to x square plus y square. Then for the sphere, to transform this into any triple integration into Cartesian to spherical polar. So it's very clear, if the sphere is there, x square plus y square plus z square is equal to a square, with center at origin and radius is a. So r, that is length of the radius vector, it is varies from 0 to a. Theta, it is this angle. Theta for the sphere, it is going like this position 0 to pi, and phi varies, that is azimuthal angle, from 0 to 2 times pi. Similarly, hemispherical surface, if it is there of the sphere, where z is greater than 0 means above the XOY plane, where r varies from 0 to a as usual, no change. Theta varies from 0 to pi by 2, because it is from this position to this position, 0 to pi by 2, and phi, as naturally it moves in this direction in 360 degree, so phi is equal to 0 to 2 times pi for the hemispherical surface of the sphere which lies above the xy plane. Similarly, octant of the sphere, if you consider, octant means only in xy plane, in this plane. So it is this surface actually of the sphere where r naturally from 0 to a on the surface of the sphere. Theta varies from 0 to pi by 2, that is this position, and phi varies from here to here for the octant of the sphere. So this is the way we are having these limits there to transform any spherical surface sphere with sphere having this particular limit to transform into spherical polar coordinates. Now, triple integration, we shall see how to define the triple integration. It is extension of double integral into third dimension. So basically, if you observe, triple integration is required to find out volume. It is concerned with the volume. Double integration is concerned with area. So volume, you can find volume of a solid, then center of gravity of a solid, moment of inertia of a solid, mass of a solid. So it is concerned with three-dimensional. So let f of xy be a continuous function defined over the solid which encloses volume V. Now, then the triple integration, it is defined as triple integration V f of xyz dx dy. dz is equal to limit delta Vr tends to 0 as n tends to infinity, summation r from 1 to n f of xr, yr, zr delta Vr. Now, how it comes here? It is limit of the sum, the function defined over the solid. Now we divide this solid into sub divisions there of rectangular parallelepiped, and we take the function f1 x1 y x1 y1 z1 defined over each of the solid. We divide this domain into number of subdivisions there, sub volumes, sub divisions, and we take the limit of sum as delta Vr tends to 0 as n tends to infinity. You are getting this triple integration. Now here you are having the limits there. How to find out limits for this? Z is equal to f1 xy to z is equal to f2 xy. These are surfaces actually, and these are curves there. Y is equal to f3x to y is equal to f4x, and the constant limits, the lines, x is equal to a to x is equal to b for f of xy, z dx dy dz. Now, where V is the volume enclosed by the solid, which is bounded by these surfaces, these curves, and the lines over there. Now, how to evaluate that? This is the procedure here. If you observe, first with respect to z, keeping x and y constant. With respect to z, f of xyz, z is equal to f1 xy to z is equal to f2 xy. Now, if you evaluate this part, then it is naturally function of x and y. I call it as capital F of xy dx dy. It is double integration now. Now, as usual, double integration means with respect to y having the variable limits f3x to f4x, f of xy dy with respect to y, and if you evaluate this, you are getting it is completely function of x there, because y is function of x. So you are getting function of x, they say phi of x dx, and finally you are integrating this with respect to x. So say integration of phi of x is psi of x. I apply upper limit and lower limit there, a to b, then by fundamental theorem, psi of b minus psi of a. This is value of the triple integration. So this is the way you can evaluate, and limit of sum, then you can evaluate this triple integration by using these techniques, these limits over there. Now let us see examples on this. Let us see examples. Show that the integral, first example, show that the triple integration V of x raised to a minus 1 y raised to b minus 1, z raised to c minus 1, dx dy dz, dx dy dz. This is equal to gamma a, gamma b, gamma c divided by gamma a plus b plus c, a plus b plus c plus 1, where or the tetrahedron bounded by x greater than 0, y greater than 0, z greater than 0, and x plus y plus z is less than or equal to 1. So you have to find out the value of this triple integration. So naturally the tetrahedron would be something like this. So if you just try to draw this tetrahedron having 4 faces there, it is something like this. So this is x-axis, y-axis and z-axis. So tetra means it is this, having the 4 faces. This plane is z is equal to 0. So this is y is equal to 0 and this is x is equal to 0. Now this is origin over here. Now and this is your plane x plus y plus z. This is equal to 1. So this is the plane. So coordinates of this point, naturally it is 1 0 0, because y is equal to 0, z is equal to 0. This plane is cutting to y-axis. So x is equal to 0, z is equal to 0, means 0 1 0. Coordinates of this point is 0 0 1 there. Now if you draw a line over here in XOY plane parallel to this and parallel to x and y axis, and erect a rectangular parallelepiped over there. So naturally at this particular point z is equal to 0. This is touching to the plane. So z is equal to, from this equation, 1 minus x minus y. So these are the limits for z there. Z is equal to 0, z is equal to 1 minus x minus y. Then y is equal to, now if you observe this, at this particular point y is equal to 0. So this is line actually x plus y is equal to 1. So y naturally it is 1 minus x, and x varies from x. You have to move this line in this particular direction. So x from 0 to 1. So like this you are getting the limits there of the tetrahedron over there. So you have to evaluate this over this tetrahedron bounded by these coordinate planes x 0, y is equal to 0, z equal to 0, x plus y plus z is less than or equal to 1. Now let us evaluate this integral with these limits. Therefore I is equal to the integral. It is something like this. Limits you have to apply. Z is equal to 0 to 1 minus x minus y. Y is equal to 0 to 1 minus x. X is equal to 0 to 1, and x raised to a minus 1, y raised to b minus 1, z raised to c minus 1, dx dy dz. Dx dy dz. So first with respect to z here, so I put this in variable separable form. X from 0 to 1, y from 0 to 1 minus x, and here it is I take x raised to a minus 1 outside, y raised to b minus 1 outside, because with respect to z we are integrating, so x and y constant. 1 minus x minus y, and this z raised to c minus 1 into dz into dx dy. It is called variable separable form. So we simplify this further. It would be something x from 0 to 1, y from 0 to 1 minus x, and x raised to a minus 1, y raised to b minus 1, and integration of this z raised to c minus 1 plus 1 means z raised to c divided by c, limits applied 0 to 1 minus x minus y dx dy. Now it is converted to double integration. So it is 1 upon c x from 0 to 1, y from 0 to 1 minus x, and x raised to a, y raised to a minus 1, y raised to b minus 1, and z means we replace upper limit, it is 1 minus x minus y bracket raised to c into dx dy. So we evaluate this now with respect to y now. So this is equal to 1 upon c, x from 0 to 1, y from 0 to 1 minus x. I take x raised to a minus 1 outside. So y raised to b minus 1, 1 minus x minus y bracket raised to c into dy, and then with respect to x finally. So I need to integrate this with respect to y, keeping x as a constant. So I will take, for the simplicity, as x from 0 to 1, I take x raised to a minus 1, and I take this 1 minus x as a some constant because it is constant there. So 0 to m I take there, and y raised to b minus 1, here m, this is temporary substitution taken, m minus y bracket raised to c into dy, and then to be integrated with respect to x. So we have to integrate this further. So it is something, so I take this over here, this is equal to 1 upon c integration x from 0 to 1, x raised to a minus 1, and this integration, it is 0 to m, where m is equal to 1 minus x over here. We have taken, it is constant, it is temporary constant there, y raised to b minus 1, and m minus y bracket raised to c into dy, and then to be integrated with respect to x. So I integrate this bracketed expression by expressing as a beta function by using the suitable substitution in order to convert 0 to 1. So put y is equal to mt, so that m is taken out, 1 minus t means we can have the form limits also 0 to 1. So dy is equal to m into dt, and limits would be for y is equal to 0, t is equal to 0, for y is equal to m, t is equal to 1. So these are the limits you are getting there. For y is equal to this, t is equal to 0, y is equal to m, t is equal to 1. So this integral will have the form 0 to 1 for x, x raised to a minus 1, and here limits 0 to 1, y is equal to mt bracket raised to b minus 1, and here m minus mt bracket raised to c, and dy, it is from here m into dt, and then to be integrated with respect to x. So we simplify this further. This is equal to 1 upon c, x from 0 to 1, x raised to a minus 1. I take this m outside. So it is m raised to b minus 1, m raised to b minus 1 plus c plus 1. So, and in the integral, you are getting 0 to 1, t raised to b minus 1, 1 minus t, bracket raised to m is taken common, bracket raised to c into dt, and this is dx. Now this is clearly expressible as a beta function. So c plus 1 minus 1 I will write down, and this is nothing but 1 upon c, 0 to 1, x raised to a minus 1. Now I resubstitute for this em, it is 1 minus x bracket raised to is plus 1 minus 1 gets cancelled, b plus c, and this is beta of bc plus 1, bc plus 1. So I simplify this further. Now beta c B C plus 1 is constant. So I take over here, it would be something 1 upon C beta of, this is constant, I take it outside, C plus 1, and integral 0 to 1 x raised to a minus 1, then 1 minus x bracket raised to b plus c into dx. Now if you simplify this, so this is 1 upon c beta of bc plus 1. This is expressible as beta function. So plus 1 and minus 1. So I will write down by basic integral of beta function, this multiplied by a b plus c plus 1. So I just simplify this and get the required RHS there, which is required. This is by relation between beta and gamma function. We write down gamma b, gamma c plus 1 divided by gamma b plus c plus 1 multiplied by gamma a, gamma b plus c plus 1 divided by gamma a plus b plus c plus 1. So this gets cancelled from here, and this is equal to 1 upon c. This also I can write down as a c into gamma c, and this c may be getting cancelled from this. So I am getting this as this gamma b, gamma c, gamma a upon gamma a plus b plus c plus 1. So that is value of this particular triple integration. So this is the way you can evaluate this triple integration by using this technique over here. Now we go for triple integration. Triple integration we have seen already. The triple integration I, it is something like this, v f of x y z f of x y z dx dy dz. So dx dy dz is the volume element actually, and if this value is 1, then you are getting this integral in this particular form, dx dy dz, dx dy dz, and this is actually the volume. So let us see some examples to calculate the volume here, because you know area is given by this formula, double integration r dx dy. It is just an extension in third dimension. This is area, this is volume. So let us see example on this. Find volume of, second example, find volume of, find volume of the sphere x square plus y square, x square plus y square plus z square is equal to a square by using triple integration. By using triple integration, by using triple integration. So solution for this problem, volume formula right now I told you, volume is given by this formula at any case, v dx dy dz, dx dy dz is dv actually the volume element, where v is the volume of surface located of the sphere. I just take this surface in z is equal to 0 in positive octant, say positive octant. So I just draw a figure for this. It would be something like this, of the sphere x, y, z. So it is this. So if you observe, it would be looking like this surface of the sphere. It is origin, and this is it part of the sphere. I will try to show here. It is this, and just I try to locate this like this. It would be looking like this, and I draw this volume element over there touching to this particular form. So it is this. Now if you observe, so it is looking like this. So this is sphere, this is x-axis, this is y-axis, this is z-axis, and a sphere, this is sphere with center at 0, 0 and radius it. Radius is a of this. Now coordinates of this point y 0, z 0, so 0, 0, a, and coordinates of this point 0, a, 0 on y-axis, and coordinates of this point is 0, 0, a. So this is octant of the sphere. So we just try to find volume of this, and we make it how many times? 8 times, and you're getting the required volume of the sphere. So I call this as expression number 1 here. Now if you observe to find out limits at this particular point, it is z is equal to 0 because this is located in XOY plane, means z is equal to 0 plane, and this one actually the surface of the sphere x square plus y square plus z square is equal to a square. So naturally z in the positive octant, it is root of a square minus x square minus y square, and this volume element to be moved from along this strip here, y is equal to 0, this, and this is boundary of the circle x square plus y square of the curve circle. So at this particular point means it is moving, y is equal to, it is boundary of the circle x square plus y square plus z square. So y is equal to 0 to y is equal to a square minus x square, and you have to move this element with this rectangular parallelepiped from y is equal to x is equal to 0 to x is equal to a, means this line. So x is equal to 0 to x is equal to a. So this is the way you are getting these limits as y is equal to z is equal to 0 to z is equal to root of a square minus x square minus y square, y is equal to 0 to y is equal to root of a square minus x square, and z is equal to, x is equal to 0 to x is equal to a. So these are the limits in the positive octant to evaluate volume of this surface located in the positive octant. So volume, using this formula, I use this formula, volume of sphere, whole sphere, complete sphere, this is equal to, I take the 8 times of this octant, volume of the octant, volume of the octant of the sphere, octant of the sphere. So I just write down this as 8 times the triple integration. I just put the limits there. Z is equal to root of a square minus x square minus y square. Then y is equal to 0 to root of a square minus x square. X is equal to 0 to a. Then dx dy dz. So I take dz over here and dx dy. So this is called variable separable form here with respect to z first, then with respect to y, and then with respect to x. So 8 times x is equal to 0 to a, y is equal to 0 to root of a square minus x square, and if you integrate this z, limits 0 to root of a square minus x square minus y square into dx dy. Now if you apply the limits, it is readily converted to double integration, x from 0 to a, y from 0 to a square minus x square, and this is root of a square minus x square minus y square dx dy. Now we put this in. So now with respect to y, x keeping constant, so 8 times x from 0 to a, I just write down this as with respect to y, so x is constant, so I will consider this as m a square minus x square, root of a square minus x square. This is m. So naturally it is m square minus y square into dy, and then with respect to x. So I use the temporary substitution here. M is equal to root of a square minus x square. So I integrate this by using the formula. So I integrate this 8 times x from 0 to a, 8 times 0 to a. Integration of this, it is something like this: y by 2 root of m square minus y square plus m square by 2 sine inverse, by using the formula sine inverse y upon m, and limits applied 0 to m into dx. So I apply the limits here. X is equal to 0 to a, then I apply the limits. Upper limit is m, lower limit is 0. So it is something like this. If you apply this is 0, so it is 0 plus m square divided by 2, and this would be 1. Sine inverse 1 is pi by 2. You are getting a lower limit, its value is 0 here, sine inverse 0, and y is equal to 0 into dx. So you may be getting this as 4 times. So here 4 2's means 2 times x from 0 to a, and this is pi into m square. M square means it is a square minus x square into dx. So we simplify this further. It would be something like this: 2 times pi x from 0 to a square minus x square into dx, and integration of this is 2 times pi a square x with respect to x minus x cube divided by 3, and limits applied 0 to a. So this is equal to, if you observe, it is 2 times pi, upper limit it is a cube minus a cube divided by 3, and lower limit its value 0 means it becomes 0. So you may be getting this as 2 times pi multiplied by 3a cube minus a cube divided by 3. So you may be getting this as 4 times pi, 4 times, this would be 2 times pi multiplied by 2 times a cube divided by 3. So this is equal to 4 times pi a cube divided by 3 is the volume of the sphere of radius a.